Okay, so the first lesson is going to be over significant figures or significant digits. Sig figs or sig digs for short. I prefer sig figs in my class. The first thing we need to discuss is an estimated digit. An estimated digit is one place value further than your measuring device is capable of recording. So that would be something like a meter stick or triple beam balance, graduated cylinder, those type of things. So let's set this up and let's just go ahead and say this is a meter stick and that we're going to measure some object, maybe a block or something, and that the block comes out this far. Okay, so if we just extend this line down here, that's where the object needs to be measured to. So this meter stick is capable of going to the 10th place. Okay, each one of these markings is 1/10. Okay, so we know that our block is at least 0.2 centimeters long, but it's less than 0.3 centimeters long. So if we were going to write down its measurement, we would say that it is 0.2 something, and that something is our estimated digit. That's the thing that we have to come up with. We have to decide how far in between 0.2 and 0.3 is that block. Okay? Okay, so if I extend the area between 0.2 and 0.3, I zoom in on it, then we can see that our red arrow actually falls right here. So our estimated digit is going to be 5. Okay. So the measuring device itself, the meter stick, is capable of reading up to the 10th place, and my estimated digit is going to go in between the 10th place so that we move out into the 100th place. And I estimate that that arrow is halfway between 0.2 and 0.3, which would put it at 0.25. So I would say that our block is 0.25 centimeters in length. Okay, so like I said, estimated digits, something that we're going to always use whenever we measure anything. Okay, so the next thing we're going to talk about are sig fig rules. Okay, this is how to decide how many significant figures a number has. And while we're on that subject, let's go ahead and define what a number is and what a digit is. Okay, this whole thing here is a number, and that number is comprised of individual digits. Okay, so the whole thing is a number, and the individual parts of that number are digits. Okay, so the first rule is that if there is a decimal in your number, so for example, let's say we've got, I don't know, 100, okay, that has a decimal in it. So if there's a decimal, you start on the left-hand side of your number, okay, and the way I remember that is that decimal has an L in it and left has an L in it. So you're going to start on the left-hand side of the number, and you're going to find the first non-zero digit. That means a digit that's not 0. So for us, that would be 1. You're going to count that number and everything after it, moving in the direction from left to right. So this number has 4 significant figures. Okay? Alright, so what if we had this number? Okay, let's apply the decimal rule. Does the number have a decimal? Yes. Find the first non-zero digit. We're going to start on the left-hand side of the number. Find the first non-zero digit. That would be 5. So how many significant figures does this number have? 1. Okay, now let's come over here and look at the no decimal rule. Alright, if your number does not have a decimal, you're going to start on the right hand side of the number, find the first non-zero digit, count that one and everything after it, moving in the direction from right to left. So for us, the first non-zero digit is 1. So how many sig figs does this number have? 1. What about this number? Let's apply our sig fig rules. Is there a decimal or no decimal? Okay, no decimal. So we'll start on the right hand side of the number, find the first non-zero digit. That would be 4. And then count that one and everything after it. So the 2, the 1, and the 1. So how many significant figures does this number have? 4. Okay, so now we know how to decide how many significant figures a number has. And this is going to become very important later on whenever we do calculations and measurements, so that we can always maintain our accuracy level throughout all of our work. We learned how to decide how many significant figures a number actually has, and this time we're going to actually do some calculations with those numbers, and now we'll have to decide how many sig figs the answer of those calculations is allowed to have. So we'll go with the multiplication division rule first. The rule is that the answer of a multiplication division problem can only contain the same number of sig figs as the number with the fewest sig figs in the problem. So what that means is, down here in our example problem, we have one number, 4,853. How many sig figs does that number have? Let's do a quick review, apply the rule that we learned last time. There is no decimal in that number, so we'll start on the right hand side, find the first non-zero digit, which would be 3, count that and everything after that, moving from right to left. So that one has 4 sig figs. Now let's check 19. How many sig figs does 19 have? Good, 2 sig figs. Alright, what that means is that since 19 has 2 sig figs and 4,853 has 4 sig figs, our answer is only allowed to have 2 significant digits because that's the number with the smallest amount of sig figs. So if you do your multiplication there, you're going to come up with 92,207 as your answer. Okay, let's see how many sig figs this has. Alright, right now it's got 5 sig figs, and we have to cut it off at 2. So 2 here, 9's the first one and 2 is the second one, and we really need to drop these. Okay, so if we rewrite this, then we can get 92,000. Alright, that is our answer with only 2 significant digits. Remember, these 3 zeros here no longer count, and so we have 2 significant digits there. I also want to point out that when we drop these numbers here, that we have to do some rounding, okay? This answer here is actually just approximate. It's rounded. You have to look one more place value over and see if that does anything to your last significant digit. So 2 does not round up, alright? It just leaves it the same. That's why this is 92,000. If this had been a 5 or higher, then we would have had to round this to here to a 3, and we would have gotten 93,000 as our answer. Okay, so now the addition-subtraction rule. This rule says that the answer can only have the same number of place values as the number with the smallest place value. So if we look in our example, we have 123.47 plus 52. Okay, so looking at both numbers, let's do the 123 number first. That number has a decimal in it, so you'll start on the left-hand side, find the first non-zero digit, count that digit, and every digit that comes after it. So This one has place value out to the hundredths place. Okay. This one over here has 2 sig figs and it stops in the ones place. Okay, so 52 is the number that has the smallest amount of place values. That means that our answer can only go out to the ones place. Okay, if you try and put more decimals in your answer, you're telling me that you're capable of being more accurate than you actually are. We're only capable of being accurate to the ones place in this problem. And if you put out to even the tenths place or the hundredths place in your answer, you're telling me you're capable of being more accurate than you actually are. Okay, so if we do the addition on that, you get 175.47 as your answer. Now again, you can't have the tenths or the hundredths place. So we need to cut it off at the ones place. Alright? You're going to look one place value further and see if that does anything to your last significant digit. And the 4 will not round the 5 up. So our final answer then is 175. So the last rule is combination. This is where you combine multiplication and division and addition and subtraction all wrapped up into one problem. The rule is that you work each part of the problem separately and you obey the previous rules. There are 2 parts to this problem. We have a multiplication division piece, or we have a multiplication piece over here, and we have a division piece over here. So we'll work each part of this problem individually. We'll do the 13.4 times 12, and we'll obey the multiplication division sig fig rule. And that one's based off of the number of sig figs. So 13.4 has how many sig figs? There's a decimal, so we start on the left-hand side, find the first non-zero digit, count it, and everything after it. So there are 3 sig figs on that one. 12 has no decimal. Start on the right hand side, find the first non-zero digit, count it, and everything after it. So this one has 2. So this is the smaller one, so our answer can only have 2 significant digits. When we do the multiplication, you get 160.8. Okay, so there are our first 2 sig figs, and that's where we have to cut it off. That doesn't mean the answer is 16. 16 is not equal to 160.8. Okay? So the only way that we can do this is by changing this into scientific notation. And if you need a review on that, you can reference that video, and I'll try and put a link in this one to that video. So you move the decimal behind the first non-zero digit and rewrite your number. Then you add times 10, and we have to decide what the exponent's going to be. And the exponent is the number of times that you moved the decimal place. So in this case it's 2. Then you have to decide if that exponent is going to be positive or negative. If the original number is greater than 1, then the exponent is positive. If the original number is less than 1, then the exponent is negative. So in this case, 160.8 is greater than 1, so our exponent is going to be a positive 2. Now, by looking at this, you can see we have 4 sig figs, not 2. So we're going to cut it off here at our second significant digit. You have to look one place value further and see if that is going to do any rounding. It will not. So our final answer for this piece is going to be 1.6 times 10 to the second. Okay, now let's come over here and do this division part of it. 19.7 has 3 sig figs, while 2.1 only has 2 sig figs. So again, we're going to have to cut our answer off at 2 significant digits. When you do this division, you get 9.38095238. Okay, well that's obviously a lot of sig figs, and we need to cut it off at 2, which is going to be at the number 3. you'll check one place value further and see if it does anything, and in this case it actually does. You're going to get 9.4 for this piece of the problem. So we'll just drop that down here. And now we're ready to do the addition piece of the puzzle. Okay? So we're going to have to obey the addition-subtraction rule here. We just got done obeying the multiplication-division for both parts of it. Now we'll do the addition-subtraction part. So that one was the one with the fewest number of place values. So for this problem, you'll notice that both of these go out to the tenths place, which means it is perfectly fine for our answer to go out to the tenths place. So if you add 1.6 times 10 to the second plus 9.4, you get 169.4 as your answer, and that goes out to the tenths place like it's supposed to. So that's our final answer, 169.4. The purpose of scientific notation is to be able to write a number that has a lot of zeros in it, either because it's really, really big or because it's really, really small, quickly, and in such a way that it's not confusing. The way this is done is by expressing the numbers in powers of 10. So the standard form for scientific notation is m times 10 to the n, okay, where m is a number that is between 1 and 10. And really, this is not 10. It's right up to 10. So like 9.99999, so on and so forth. Okay? So scientific notation, you would never have a number in scientific notation that looked like this. That is completely wrong, because this m value is not between 1 and 9.99999. So this whole, that's wrong. Okay? N is the exponent, and it's equal to the number of times that the decimal point was moved. N is positive when the original number is greater than 1. Okay, so n is positive if m is greater than 1, and n is negative if m is less than 1. Okay, and that m, I'm talking about the original number. So let's look at an example. Let's write this number in scientific notation. Okay, so first step, find the decimal, and then you're going to move the decimal so that it's behind the first non-zero digit. Okay, so here's the decimal, and it has to be moved behind the first non-zero digit. Okay, so that transforms the number into 5.2346876. And after we've moved the decimal place, we'll put times 10, because we've changed it into scientific notation. And now n is the number of times that we moved the decimal point. So count how many times that we moved it, and we get 4. So our exponent is going to be 4. Now we have to decide if that 4 is going to be a positive or a negative 4. So we'll look at that original number again. I'll put it over here so it's kind of cleaned up a little bit. So we put it over here, and is this original number greater than 1, or is it less than 1? Okay, so obviously this is greater than 1, which means we're going to have a positive exponent. Okay, so our final answer here for this number being in scientific notation would be this. Okay? Now, we can have a really, really small number also. We could do something like this. And we might want to change that into scientific notation. So again, you're going to find the decimal point, okay, and you are going to move it so that it is behind the first non-zero digit. So there's our decimal point, and now we're going to move it so that it's behind the first non-zero digit. So now we rewrite the number 5.2346876. Okay, up until this point it looks exactly like the previous example, and we're going to put our times 10, and now we have to figure out what our exponent is going to be by figuring out how many times we moved the decimal. Okay, so it looks like we've moved the decimal 7 times, so we know the exponent is going to be 7, but we don't know if it's positive or negative yet. Is the original number larger than 1 or less than 1? Good. This one is less than 1, so this is going to be times 10 to the negative 7. Alright, so that gives us our final answer there for that one. And that's really all there is to scientific notation. Now, the purpose of scientific notation that we're really going to take advantage of is being able to write specific numbers with a specific amount of significant digits. Okay, so for example, this 100 here, how many sig figs does it have? Okay, so there's no decimal, so we're going to start on the right hand side and find the first non-zero digit. So this has 1 sig fig. Okay, what about this version of 100? Okay, this one does have a decimal, so we're going to start on the left hand side and find the first non-zero digit and count everything after it. So this one has 4 sig figs. Or you could even do one like this and just put a decimal point there and again find the sig figs. This one has 3 sig figs. But what if a problem that we worked required that the answer only have 2 significant digits? What if we had a given that started with 2 sig figs, and therefore our answer had to have 2 sig figs, and the answer happened to be 100? How can we write 100 with only 2 significant digits? You've seen 3 examples up here at the top, and none of them are 2 sig figs. There is no way to write the number 100 with 2 sig figs unless you change it into scientific notation. So, you would take 100, okay, and if there's not a decimal, then you know that the decimal is always at the far right of the number, okay, and you are going to move that decimal behind the first non-zero digit and rewrite it, okay. So 1.00 times 10, and then how many times did we move it? 2. Is the number 100 larger than 1 or less than 1? Obviously it's larger, so that's a positive 2. Now this has 3 sig figs. We only want 2 sig figs, so our final answer then becomes 1.0 times 10 to the second. That is the number 100 with just 2 significant digits. Okay, let's check that out, make sure that you understand. That times 10 to the second, we can undo that. We can go 1, 2, and fill in that little well with another 0. When we do that, we change it back into standard form, and we get 100. You drop the times 10 part off. So this does equal 100. Those are equal to each other. Okay, so this provides us, scientific notation provides us with a way to get the appropriate number of significant digits when a problem requires that. So if there's no other way to write it, change it into scientific notation. You need to be able to go back and forth between scientific notation and standard notation. Okay, the next thing to consider is when you have two numbers that are in scientific notation and they need to be multiplied. Now, we obviously have calculators that can do this for us extremely quickly. However, we as humans, we are prone to error. So it is highly likely that at some point you're going to be clicking on the calculator buttons and you're going to hit a stray button. And then you won't know that you did that. You'll keep going. You hit the enter button, and whatever pops up on that screen you have been trained to believe is true. Okay? And you'll write that down blindly, thinking you got the answer right the whole time because that's what the calculator told you, when in fact you are completely wrong. So you need to be able to understand or to tell when the calculator is giving you garbage before it happens. Alright? So here's how you do that. In order to multiply two numbers that are in scientific notation, you're going to multiply the m part of the number, and then you are going to add the scientific notation part, the exponents, get added together. Okay? And this is just regular old algebra. You've done it before. When two numbers are on the same base, then you can add their exponents. So for example, let's say that we had 5.6 times 10 to the 12th, okay, and we can multiply that by 7.102 times 10 to the 4th. Okay, so let's figure out what that's going to be. The first thing that you're going to do is multiply the 5.6 by the 7.102. Okay, and when you do that, you're going to get 39.7712. Okay, so that's the multiplication part. Then you're going to put your times 10. The next step is to add their exponents together. So that gives us 16. Okay, now I told you previously that you cannot have an m that is not between 1 and 10, or 1 and 9.999, because then you're not on a base 10 scale anymore. So what we have to do is take that decimal and move it back one more spot, and that's going to increase the exponent over here by one more. So we get 3.97712 times 10 to the 17th. Now, if you check that in your calculator by using your times 10 function, then you will see that that is the correct answer. And so you would have some idea of that before you ever typed it in. The easiest thing to do, I think, is to check the exponents part first. You know that whatever your answer is going to have to be times 10 to the 16, and then you could either go one less or one more for this circumstance down here, either in case the number happens to be larger than, or it's larger than the 1 to 10 range, or maybe it's smaller than the 1 to 10 range. Your exponent could drop by 1, or it could raise by 1. In this case, it raised from 16 to 17. If this number over here had been less than 1, then this number here, the 16, would have dropped to a 15 instead. So anything that your calculator tells you from times 10 to the 15, times 10 to the 16, or times 10 to the 17, you would accept as a possible outcome. That would be reasonable. But if the calculator gave us like times 10 to the 24th, that's not reasonable. Okay, and you should recognize that that's garbage. You hit something wrong in the calculator and you need to try it again. Okay, now let's look at division. When you are dividing two numbers that are represented in scientific notation, you're going to do the same thing. You're going to divide the m part of the scientific notation, and then instead of adding the exponents, you'll subtract them. So let's see what happens if I use the same example from the problem above, except I divide it. So I do the 5.6 times 10 to the 12th, and I divide that by 7.102 times 10 to the 4th. Okay, well, again, you're going to take the m piece of the number and you're going to divide it. And you should get 0.788510 okay, and then we'll put the times 10 on there, and now we will subtract. The 12 minus 4 is 8, so this is our answer, except it's not between 1 and 10. The m part of our number over here is less than 1, so you're going to have to again grab the decimal and move it behind the first non-zero digit. So now our number becomes 7.885103 times 10 to the, and then since we had to move the number or the decimal point towards the right because the original number is smaller, then we have to subtract 1 away from our exponent. So this is going to become a 7. And if you type that into your calculator, you will see that that is, in fact, the correct answer. And as you get more and more comfortable with this, you will recognize up here at the top in the beginning that you are dividing a number. You are dividing a smaller number by a bigger number, so you're going to get a decimal point. Now, of course, I'm just talking about the m part of the number. Obviously, we know that something that's times 10 to the 12th is larger than something that's times 10 to the 4th. But the m piece of both of these numbers is what I'm referring to. So 5.6 is smaller than 7.102. So you should have recognized that our answer was going to be smaller than 1, which means whatever exponent we got, we were going to have to subtract away from it. Okay? And then the opposite is true for the above example. Okay, so let's see if you can apply our new knowledge. Let's say that we have the following numbers that need to be multiplied by each other. Okay, I want you to do this without a graphing calculator or without your scientific calculator. You can use a regular standard calculator if you need to in order to multiply your m parts and then add your exponents together. So take a couple of seconds to do that. If you need to, pause the video and then I'll put the answer on the screen here in just a second. Okay, and you should have come up with 4.152 times 10 to the 10. Okay, if you didn't get that right, then go back and review what we just watched and see where you missed. Try this next one. What if we have 5.0 times 10 to the 15th divided by 2.5 times 10 to the 7th? Okay, try that one. I'll put the answer on the screen in just a second. Okay, we get 2 times 10 to the 8th. Now this one should have been really easy to do in your head. Alright, 5 divided by 2.5 is 2, because 2.5 is exactly 1/2 of 5. And then 15 minus 7 gives us 8. So 2 times 10 to the 8th, and that one should have been really easy. Accuracy and precision. Okay, significant digits was the last topic that we discussed, and accuracy and precision is the whole reason that significant digits even exists. Okay, the significant digits is a way that we standardize how things are measured and how our answers are reported. And the reason that we have to do that standardizing is so that we can always make sure that our results are both accurate and precise. And so let's go ahead and define accuracy and precision so that we can further explain the relation to significant digits. Accuracy is how close a value is to the true or accepted value. And precision is how close a value is to a set of data. So in accuracy, where we have a true or accepted value, we're saying that we as the scientific community, after doing a bunch of experiments and getting the same results over and over and over again, we have all decided that that will be the true or accepted value. So for example, the density of water. The accepted value for that is 1 gram per milliliter. Okay, no matter where you go on Earth, that's the density of water, the accepted value. So if you are doing an experiment measuring the density of water for yourself, and you were getting values that weren't 1 gram per milliliter, then you would be able to say that you're not getting close to the accepted value. Now, as far as significant digits are concerned, it's really 1.00 grams per milliliter. So we have 3 significant digits in our accepted value. That way, when you're doing your experiment, if you come up with 1.02 grams per milliliter, for example, you were good on your measurement for the first and the second significant digit. It's just that the third one is where you lost accuracy. Okay, so the accuracy and precision and the sig figs really do tie into each other, and the whole purpose of having significant digits is so that we can make sure we're maintaining our accuracy. So whatever measuring device you were using that was great for the first sig fig and great for the second one, it faltered on that third one. So you would need to, if it was important for you to be significant out to the hundredths place, you need to get a different measuring device or fix the one you've got. If you only need to be accurate to the tenths place, then your current measuring device is good enough, and you don't need to change anything at all, even though it's not good in the hundredths place. Alright, now let's talk about precision. How close a value is to a set of data. Okay, so let's pretend that a student, Mike, and another student, Allison, are both performing an experiment. They are going to go ahead and get the density of water. So I'll put up here what our accepted value for the density of water is again. Alright, and this time I'll include 3 sig figs. Okay, so they go in there, they have to get a certain amount of water, and then they're going to take the mass of that water, take the volume of the water, and divide, because we know that density is equal to mass divided by volume. Alright, so let's say that Mike does this, and his first trial gives him a density of water of 1.01 grams per milliliter. And then he does the trial again with a new mass and a new volume of water, and he gets 1.00 grams per milliliter. And then he does it again, and he gets 0.980 grams per milliliter. Okay, and then Allison performs this experiment, and she gets 0.68 grams per milliliter, and then 2.03 grams per milliliter, and then finally 1.53 grams per milliliter. Okay, well, let's just talk about the precision part of this data first. Let's go look at Mike's data again. If you'll notice, he's got 1.011 and 0.980. All three of those trials are very close to each other. Okay? 1.01 is really close to 1. And 1 and 1.01 are really close to 0.98. Okay, so all three of his sets of data are extremely close to each other. That means that Mike was very precise when he did his experiment. Alright, now let's go ahead and look at the data that Allison got. Okay, her data, 0.68 is nowhere near 2.03. Alright, that is way far apart. And 2.03 is not close to 1.53. And 1.53 is certainly not close to 0.68. So none of her data is precise. Alright. Now let's look at the accuracy aspect of their data. Remember that the density of water, the accepted or true value, is 1 gram per milliliter. Now look at Mike's data. It is all very close to 1. In fact, this one is right on it. That one is accurate up to the 10th place, and it only faltered in the 100th place, so that's really close. And then 0.980 is extremely close to 1. Alright, so these results over here are accurate, or are very close to being accurate. Now if you look at Allison's results, none of her information is accurate because all of her values are extremely far away from 1 gram per milliliter. Oftentimes when we talk about accuracy and precision in science, we get the bullseye example, so I'll go ahead and continue with that tradition. The first thing, let's go ahead and say that this first bullseye, and I'll number these so you know which ones I'm talking about. The first bullseye, let's say that a person shoots at the target, which is the center of the bullseye, and we'll say that that's the most accurate position, is the center of the bullseye. That's where you want it to hit. So they shoot at the bullseye and they get close to the center every single time, but all of their shots are spread out from each other. So in this case, we can say that they were accurate because they got close to the center every time, but they were not precise because none of their shots were close to each other. And remember, precision is about having all of your data being close to each other, and accurate is about having all of your data close to the accepted value. Alright, now let's say that this middle one, they shoot and all of their shots make it into the bullseye, and all of their shots are very close to each other. So in this case, they were both accurate and they were precise. Alright, now over here, let's say that they shot at the target and all of their data is really close to each other, but none of it is even remotely close to the bullseye. So here, they were not accurate, but they were precise. Okay, so those are your three possible outcomes. Now let's talk about bias. Okay, bias is anything that causes the data to be swayed or be less accurate, be further away from the true or accepted value. Okay, so what you're looking at right now is a triple beam balance. And on a triple beam balance, we have two lines. You have a line over here, and you have a line here. And this is the zero line. So those two lines have to match each other before you ever put anything over on the measurement tray. Okay, so notice that it is empty over here. Now what if the two zero marks did not match up before you put something on the tray? Let's say the tray is empty, but your zero mark is actually down here, like this piece right here is down at this level. Okay, so what that's showing is that there is less than no mass on the tray. Alright, so this is going to make any measurement that you take from this triple beam balance appear lighter than it actually is. And that introduces bias into your results. It causes them to be less accurate, you know, or the tray could start out at this level, and that would show that there is mass on it even though there isn't. So all of your results would appear to have more mass than they actually do. Let's go back and look at Allison's results for a second. If we look at Allison's results, remember she was not accurate or precise. Her information, her data is all over the place. There is a reason for that. Okay, so when Allison writes up her report over her experiment, she needs to give some possible reasons on why her data is nowhere close to each other. She needs to say something about either the triple beam balance maybe didn't start out at 0 like it should have, or maybe her graduated cylinder had soap residue left in it, and because of that it disturbed the surface tension of the water, and so it messed up her reading in that way. So looking at this graduated cylinder on the left, you can see that the water forms this concave shape, and concave means a shape like this. Alright, so water does that. That's one of the properties of water, and it happens because of some forces that we'll talk about later on in the course. But when you read on a graduated cylinder, you read from the bottom, which is called the meniscus. Okay, that's the correct way to read the level of liquid in the graduated cylinder. Now if you look over here at this graduated cylinder on the right that's got soap residue in it, you'll notice that the water, or whatever liquid that is in there, is not making that convex shape. It's just a straight line. That's because the soap has disrupted the surface tension of the water so that it can't do that. Alright, and so the results that you read from this graduated cylinder will be wrong. The water level is actually supposed to be at a different reading. That whatever results you get from that graduated cylinder will be incorrect. So that's bias in the graduated cylinder reading. And you can have bias introduced into any measurement you take, from a beaker, a burette, a graduated cylinder, a triple beam balance, a scale, anything, a meter stick. There can be bias in there for some reason or another. So it's your job as a good science student to look for these kinds of things, try and avoid them if you can, and if you can't, include them in your lab write-ups so that you can justify why your results weren't accurate or weren't precise. The SI system, or the metric system, or the international system of units. The reason it's SI is from the French language, it's Système d'International. Anyways, this is the system of units that almost the whole world uses. America, or the United States, is the only place that does not use the SI system as its primary source of measurement. So we use things like feet and gallons and pounds and stuff like that, and in the metric system we use grams and meters and liters. So in the scientific community we use the SI system because the majority of the world uses the SI system, and that allows us to compare our experiments and the data that we get from our experiments to the results of scientists from other countries. the whole point of science is that it is repeatable. Okay, when somebody performs an experiment and they get a result, we don't just say, oh, okay, cool, we figured it out. Somebody else from somewhere else has to be able to duplicate your results. It has to be duplicated many, many times before we finally say, okay, that wasn't just a fluke. It can be repeated. It happens over and over and over again. So anyways, in order for us to compare results, we all agree to use the same system, and the metric system is the one that we agree to use. A famous case, as you can see on your screen, where some scientists forgot to use the metric system was for NASA's orbiter mission to Mars. That ended up costing them $125 million because one team of scientists used the metric system like they were supposed to, and another team of scientists used the English system. And then when they compared or sent information to each other, no party, neither one of them, realized that the other one was using different units. And so because of that, that operation didn't go according to plan. So anyways, it's always important to make sure that you're using the metric system in any scientific calculation that you do. Alright, so let's go ahead and talk then about what comprises the metric system. Okay, we have to begin with our base units, which I have boxed here in blue. And the M stands for mass. The L stands for liters, and the G stands for grams. Okay, so the reason these are called base units is because they're the simplest form of the unit itself. The other distinctions are either smaller or larger than the base unit. Okay, let's just go ahead and say, I apologize, I just noticed a problem here. This M does not stand for mass. It stands for meter. Okay, so meters are the unit that goes with distance. Liters are the unit that goes with volume. And gram is the unit that goes with mass. Sorry about that. Okay, let's go ahead and define mass for a second. Mass is how much matter an object is, and it is different from weight. Weight is how much gravity is pulling on an object's mass. So your weight can change, but your mass will not. Okay, and what I'm talking about is like if you were traveling from the Earth to the Moon. You as a person have the ability to lose weight and mass. So like if you go on a diet and you get skinny, the reason you're getting skinny is because you are losing weight and losing mass. You do not have the same amount of atoms as you did before. But let's say that you weigh, I don't know, 200 pounds here on Earth, and you get into a rocket and you go to the moon. You will not weigh 200 pounds on the moon. You'll weigh less, but you didn't lose any mass during your trip. You still have the same amount of mass as you did before. And the reason for that is because there's less gravity on the moon than there is on the Earth. Okay, I just need to make that distinction because in this class you will not weigh anything. When you go back into the lab and you are collecting data, you will always be collecting the mass of your objects. And some of you will be in the habit of saying, I'm going to weigh this or I need to weigh that, and I will just stop and correct you and tell you that you're not weighing anything, you are massing something. So you need to know what the difference is between those two. Alright, back to the metric system. Again, remember that the base units are boxed in blue. Now let's look up here at the larger selection. We have kilo, we have hecto, and we have deca. Now these are all prefixes that you add to your base unit. So you can have a kilometer, or you can have a kiloliter, or you could have a kilogram. You can have any variation of these base units by just adding on your prefix. And all of these things show that it is larger than the base unit. A kilometer, for example, is going to be 1,000 times larger than a meter. A hectometer will be 100 times larger, and a decameter is going to be 10 times larger. That means that all your base units are going to be 1. Okay, so the kilometer is 1,000 times more than 1, and so on and so forth. Alright, so this kind of leads us into a bit of a confusion for some students that we'll go ahead and clear up. Is we need to decide what is equal. Is 1 meter equal to 1,000 kilometers, or is 1,000 meters equal to 1 kilometer? Here's how you answer that question. It's with the word larger over here to the side, okay? I always ask myself, can a bunch of large things fit into one small thing, or can a bunch of small things fit into a large thing? Okay, and now obviously the answer is that a bunch of small things fit into the large thing. So that means that it takes 1,000 meters, the base unit, to equal 1 kilometer. Okay, now I can understand why it's confusing, because suddenly 1,000 goes with meter, and down here I've told you that the base unit is 1. But remember that this 1,000 up here at the top next to kilometer is there because it's 1,000 times greater than 1. Okay, that means it's going to take 1,000 of these small base units to equal 1 of these large units. Okay. Alright, now down to the smaller versions of the base unit. We have deci, we have centi, and we have milli. Okay, let's see, centi you might be familiar with, like century. Alright, it is 100 years. Or milli, like millennium, 1,000 years, not a million years. Or deci, like, deca up at the top, like decade, which is 10 years. So these all kind of have, or these words that we use on a daily basis have ties back into the metric system. Deci is 1/10 of the base unit. Centi is 1/100th, and milli is 1/1000th. Okay, so that means that deci is 0.1. If you were to multiply 1 times 0.1, you would be dividing it by 10. Alright, or we could have down here for centi, we get 0.01, and milli is 0.001. Alright, if you'll notice, up here on the top we were multiplying by these values, and on the bottom we are dividing by these values. Okay, so that gives us our general look into the SI system. Now you are going to have to memorize this system, and there is a trick or whatever, and I'm sure you've learned it before, to memorize each of these names in the system. When I was in school, it was King Henry danced merrily down Center Main. But that kind of leaves out these two base units here, liter and gram. So there's a new one. King Henry dunked many large glazed donuts in chocolate milk. That's one that you could use to help you memorize the metric system. Whichever one you choose or make up your own, the point is you're going to have to memorize this system. Not only the names and the base units, but how big they are. You need to know that kilo is 1,000 times greater than any of the base units, and need to be able to come up with this conversion factor here between any of the units in the SI system. In addition to that, there are 3 English to metric units that you are going to have to memorize. Alright, so here they are. 1 inch equals 2.54 centimeters, and 1.06 quarts equals 1 liter, and 1 pound is equal to 454 grams. Okay, those are your English to metric conversion factors, and they too must be memorized. Percent error, which the official definition is how far off the accepted value your data is. Basically, this is a measure of how wrong you were, or how bad your results are, if you want to put it like that. It really doesn't measure how good or bad you did your experiment. It just measures how good or bad your results are compared to what they should have been. And it's used as a guide to see whether or not something is wrong with your experimental setup. Okay, so it doesn't always have to be negligence on the part of the scientist, but it could show the scientist that maybe there's something wrong with the equipment's faulty in some way, or maybe there's bias somewhere in the equipment that needs to be addressed. Alright, so let's go ahead and work through the formula real quick, and then we'll do an example. So percent error is the theoretical value. Theoretical just means the accepted value we talked about earlier. For example, we had talked about the density of water having an accepted value of 1.00 grams per milliliter. That is the accepted or theoretical value that all of the scientific community agrees upon. Alright, then we have the experimental value. That's what you would get when you run your experiment. So whatever you got in the lab is your experimental value. Okay, so let's look at the previous example from the earlier video where we ran an experiment on the density of water. Okay, so here we have Mike and Allison and their data again. So we have 2 sets of data. Now, looking up at the formula here, we have a spot for the theoretical value and we have a spot for the experimental value. Okay, we do not have a spot for 3 separate trials worth of data. So there are 2 approaches to this. You could find the percent error for each trial individually, or you could find the percent error for the entire experiment by taking the average of all of the trials. And I think that that's the method that we'll go with. Okay, so let's tackle Mike's data first. So you'll see down here that I have averaged Mike's density data. So this is the average density of water that Mike came up with. And so we'll use that in our percent error formula. Alright, so we've plugged in the information into the percent error formula. You've got the theoretical value, which is 1 gram per milliliter. We've got our experimental value, which is the average density that we get from Mike's data, all divided by the theoretical or accepted value down here on the bottom again. You'll also notice that this formula is in between absolute value bars. So it is impossible to get a negative percent error. And the reason for that is because nobody's perfect. We don't live in a perfect world, so you will never have 0% error, and obviously you can't have less than 0% error. You will always have some kind of error in your experiment. So when we crunch the numbers, we get 0.33 repeating percent error. So that's a really good result there. That means we were not that wrong, or at least Mike was pretty good in his experiment. Doesn't seem to be much wrong with his equipment, and he must have been very dutiful during the experiment itself. Alright, now let's look at Allison's data. Okay, so I've taken Allison's results and gotten her average density up here at the top, and that's what we have placed into the percent error formula as the experimental value, and we have 1 gram per milliliter again as the theoretical or accepted value. So when we crunch the numbers on this one, we get 41% error. Okay, and the 41% here is only 2 significant digits because we had 0.68 up here, and that only had 2 significant digits in it. Actually, coming back up here to Mike's data, there should be one more 3 in here because all of our initial data points had 3 significant digits for Mike's data. So you'll notice, obviously, that Allison's results are quite a bit, or her percent error is quite a bit higher than Mike's is. And obviously, like we said at the beginning, the reason for that could be many things. It doesn't mean that Allison did a bad job necessarily. It just means that there might be some problems with her experimental setup, and she'll need to go in and take a look at that and then redo her experiment so that she can bring her percent error back down to a reasonable level, because 41% is not reasonable. Okay, let's start with the next topic, which is called dimensional analysis. Don't let the name fool you. Dimensions are another word for unit, and so all we're going to be doing is taking a look at the units that go along with a different problem. In the last video, I mentioned the word conversion factor. And so now let's define that. Conversion factors are just when something equals something else. So for example, $1 equals 4 quarters, or 1 quarter equals 5 nickels. That would be an example of a conversion factor. And hopefully you're familiar with that concept in your everyday life. Gasoline, the price of gasoline, $3 and whatever cents per gallon. Another way of saying that is $3.12 is equal to 1 gallon of gas. Or the price of milk, or any time that you're going to be exchanging one thing for another thing, that's a conversion factor. Alright, the next thing that we're going to talk about is called the given. Alright, the given is a piece of information that is not set equal to anything else, which means that it's not a conversion factor. It's used to start the problem off, and it's where the sig figs come from for your answer. And hopefully you've already watched the sig fig video, so when we're trying to come up with how many significant digits our answer has, you look at the given and see how many sig figs it has, and that's how many your answer has to have. Okay, so steps to successfully complete a dimensional analysis problem. First thing is you're going to want to put the given over 1. And remember, anything over 1 is still itself, so you're not changing the problem when you do that. Step 2, use any conversion factors that you're given, and also any ones that you were told to memorize or that you just know because you've lived on this planet. Like, for instance, 1 foot equals 12 inches. And so on and so forth. Step 3, stop when the last unit is the one that the problem is asking you to convert to. If the problem asks you to convert feet to inches and you end up in units of inches, then you're done with the problem. So don't keep trying to look for things to do. You're done. And then step 4, multiply across the top and divide across the bottom, and I'll tell you what that means when we work an example problem here in just a second. Alright, so here's a question. How many quarters are in $5? Okay, the first thing that we need to do is identify what's the given in the problem. Remember, the given is something that's not equal to something else. So for us, reading this question, it's obviously going to be $5. That's not associated with any other number. So you're going to put the given over 1. And make sure that you include the units when you do that. You're going to put this little dot, which means to multiply, and put another fraction bar. The next step was that you had to cancel out units top and bottom using the conversion factors that you have available. So the conversion factor that we have available is that $1 equals 4 quarters and 1 quarter equals 5 nickels. In this case, we're asked to convert to quarters, so we're going to want to use our first conversion factor here. Now we have to place it on this second fraction bar here in such a way that the units will cancel out, top and bottom. So I notice that I've got dollar signs on top in the given, which means I'm going to have dollar signs on bottom in our conversion factor. So I'm going to go ahead and put that here, and then you say what that's equal to on top. Okay, so now you'll notice that the dollar sign cancels the dollar sign top and bottom, and I'll be left with units of quarters, which is what the problem asked me for. So I'm done. All I have to do now is multiply across the top and divide across the bottom. So 5 times 4 is 20, and 20 divided by 1 is still 20, so we're left with 20 quarters. 20 quarters is equal to $5. Okay, so let's take it another step. How many nickels are in $5? Okay, again, you're going to want to put your given over 1, and our given is still $5. Put our little multiply sign and put another fraction bar. And we're going to have to continue to use our conversion factors. So again, our conversion factors were that $1 is equal to 4 quarters, and that 1 quarter is equal to 5 nickels. Okay, so on this second step here, I still have to arrange the units so that they cancel out top and bottom. Since I've got dollar signs on top, I'm going to have to put dollar signs on bottom. So again, the $1 goes on bottom. Now, the conversion factor that I have up here that involves dollars is $1 equals 4 quarters. I'm looking for nickels. Okay, that doesn't mean that I don't use that conversion factor, it just means I'm not done yet once I've used it. So I'm going to put that $1 equals 4 quarters in there, and that conversion factor has been used. Since quarters is the unit that I'm in right now, but I'm looking for nickels, I have to keep going. So we're going to put another multiply sign, another bar, and go get another conversion factor to put in here. Okay, now notice that we've got quarters on top, which means that quarters has to go on bottom. So I go find a conversion factor that involves quarters, and I get 1 quarter equals 5 nickels. So 1 quarter equals 5 nickels. Alright, now I'm in units of nickels, which is what I wanted to be in. So I'm done with the problem. You can see that dollars cancels dollars, quarters cancels quarters, and we'll be left in units of nickels. So we're ready to do the math. Multiply across the top, divide across the bottom. 5 times 4 is 20, and 20 times 5 is 100. So we're left with 100 nickels as our answer. Alright, so these two are just really simple examples of dimensional analysis, and that's what this whole first video is intended to be. Is just, this is part 1. We're not done with this. This is just the most simple type of dimensional analysis problem that we have. And so in the next video we will move on to some more complex dimensional analysis. The reason I say that this is a simple version is because it only involves one unit in each of our questions. Notice that it was always $5 going to some other unit. But in life we can run into numbers that have multiple units, like miles per hour, or for density, grams per milliliter. So those are what we call complex units when they have more than one unit that makes them up. Derived units. Okay, a derived unit is a unit that's made up of 2 or more other units. So as you can see down here in our example, we've got miles per hour, so that involves the unit of miles and hours, and we want to convert that into meters per second, so that involves the unit of meters and seconds. So both of those are derived units. So let's go ahead and jump right in on how to solve this problem. The steps are all the same. the first thing you have to do is identify the given, and obviously your given is going to be 43 miles per hour. However, you're not going to put 43 miles per hour over 1. That is not the correct way to go about this. Instead, you're going to put 43 miles, that's the first unit in our derived unit, over 1 hour. That's the second unit in our derived unit. Let's take a look at an example for a second. Let's say that gas today costs $3.52 per gallon. Okay? This per sign right here, this division sign, that's another way of saying equals to. Alright, so anytime that you see per, you see that division sign between something, then you can go ahead and understand that that means equals to. Alright, so $3.52 is equal to 1 gallon of gas. Alright, on the other side of this per symbol up here is the number 1. Alright, it's always 1 of that other unit. So if you are driving 52 miles per hour, this per here tells us that you're actually driving 52 miles for every 1 hour of time that elapses. Okay, so 52 miles is equal to 1 hour, and remember that number is always 1 on the other side of the per symbol. So that's where this 1 comes from here for hours, 43 miles for every 1 hour. Alright, we're going to put our little dot in our fraction bar just like we have done. And now, this is the only part where we add an extra step. We don't even change the steps, we just add one more. You're going to pick one unit to deal with at a time. Alright, so I think I'll go ahead and pick miles first. So if I've got miles on top, I have to have miles on bottom. And now it's time to go get some conversion factors. I'm going to go ahead and list all the conversion factors out on the screen. So let's grab a conversion factor that deals with miles. Okay, and it looks like this first one deals with miles. Okay, so 1 mile is equal to 5,280 feet. Okay, so this first one has been used. That one's done. Obviously, we are in feet, which is not the correct unit. We need to be in meters, so we're going to keep going. So we'll add another dot and another bar. And since we have feet on top, you have to have feet on bottom. So we're going to come back down here and find another conversion factor that deals with feet. And that looks like the second one. So 1 foot equals 12 inches. We're not there yet, so we're going to keep going by adding another dot and another bar. And since I've got inches on top, I need inches on bottom. And it looks like this one deals with inches. So 1 inch equals 2.54 centimeters. Okay, now you might be asking yourself or saying, well, wait a second. This conversion factor has inches in it, and this one has inches in it. How do I know that I was supposed to use this one and not this one over here? That's because the second one here was already used in this example problem right here. But that one's done, so it can't be used again. Alright, the next one, we've got centimeters on top. So we have to have centimeters on bottom. So we're going to come over here and let me cross that one out. And we see this one has centimeters in it. So we see that 100 centimeters equals 1 meter. And that is the unit that we are trying to get to for distance, is meters. So we're done with the distance part. Notice, miles cancels miles. Feet cancels feet, inches cancels inches, centimeters cancels centimeters, and we're left with meters in the numerator, which is what we want. Now we've got to get seconds in the denominator. So we're going to add another multiplication dot and another bar. Now here's the only part that I'm going to use the word tricky, even though this is not tricky at all. But in the beginning it tends to throw you because it's opposite of what you're used to doing. You are, at this point, used to looking at a unit on top and matching it up with a unit on bottom. Okay? But now we're going to look at a unit on bottom and match it with a unit on top. Okay? So since hours are in the bottom, we're going to have to put hours in the top in order for them to cancel out, top and bottom. Alright, so let's come find a conversion factor that deals with hours. And we see this one right here. Okay, 1 hour is equal to 60 minutes. Okay, so that one's done. Okay, now we've got minutes on bottom, but we're trying to get seconds on the bottom. So we add another dot and another bar. And we say that we've got minutes on bottom, so we need minutes on top. And then we'll use our last conversion factor here, and it deals with minutes. It says that 1 minute is equal to 60 seconds. Okay, so notice that hours on bottom cancels hours on top, and minutes on bottom cancels minutes on top, and we're left with seconds on bottom, which is exactly what we wanted. Okay, so overall we've got meters per second. Okay, so we are in the unit that we want. It's time to multiply across the top and divide across the bottom. Now notice I ran out of room lengthwise, so I kind of had to make a secondary little thing here. So we're going to say 43 times 5,280 in your calculator and hit the equal sign or the enter button. Then multiply that number by 12 and hit the equals button. Then multiply that by 2.54. And then the rest of the stuff on top is ones, even down here in our secondary area. So we can just ignore that. Now we're going to have to divide by the things on bottom. So the first thing that we see to divide by other than 1 is 100. So divide by 100 and hit the equal sign. Then divide by 60 and hit the equal sign. And then divide by 60 again and hit the equal sign. And if you do all of that correctly, you end up with 19 meters per second. And I am taking significant digits into account. In your calculator, you should get 19.22272, so on and so forth. But notice up here in the given that we have a significant digit here and a significant digit here. So there's only 2 sig figs, which means our answer can only have 2 sig figs. So that's why we stopped at 19, because the 2 does not round the 9 up. So 19 meters per second is the answer. And that actually gives us a new conversion factor. That would be a weird conversion factor to have, but it's true. We could say that 43 miles per hour is equal to 19 meters per second, and that could be a conversion factor in a future problem. Again, that would be a weird one to have, but it would work. The next type of problem that we have to learn how to work with is when our units have exponents, or I should say exponents other than 1. Up until now, we have worked with things like feet to inches, or we've worked with miles per hour to meters per second, and all of these actually have units or exponents to the first power. Okay, and remember, if something's raised to the first power, then it's just itself, so we can ignore it. But now we are dealing with units that have exponents other than 1. So it can be squared, it can be cubed, and so on and so forth. Alright, so let's just dive right in. The first thing you're going to do is just like we've done in all the rest of the problems. You've got to put the given over 1. And so we identify that the unit here, or excuse me, that the given here is 16 inches squared. So we're going to put 16 inches squared over 1. Put our little multiply sign and then put our dot. Okay, so right off the bat, you can see if you've got inches squared on top, you're going to have inches squared on bottom. That looks like a 3, not a 2. Let me change that. Okay. And then we need to go ahead and list some conversion factors. Okay, so the only conversion factor that we need is this one that you were told to memorize a while back. 1 inch equals 2.54 centimeters. Now, we can't just plug that in up here in this second bar, and that's because this is just inches, and we have inches squared that we have to deal with. Okay, so what we're going to do then is we're going to go ahead and put our 1 inch in here, and then in parentheses say that we're going to square that. And then on top, we're going to put our 2.54 centimeters, and we have to square that too. Since we squared the one on the bottom, you have to square the one on the top. And then we just do some math individually here. We know that 1 inch times 1 inch equals 1 inch squared. Okay, and then we come up here on top and we say 2.54 centimeters times 2.54 centimeters equals 6.4516 centimeters squared. Okay, so now we could rewrite this problem. We could say 16 inches squared over 1, and then we could say 1 inch squared equals 6.4516 centimeters squared on top. And inches squared cancels inches squared, and we'll be left in units of centimeters squared, which is exactly what we want up here. So we're done. We're ready to multiply across the top and divide across the bottom. And we get 103.2256 centimeters squared. Now, let's do our significant digits. How many significant digits do we have in the number 16 up here? Okay, let's review our rules. Is there a decimal or no decimal? Okay, there's no decimal, which means you start counting on the right-hand side. Find the first non-zero digit, which would be 6, and then count everything over from that. So that's 1, 2. There are 2 significant digits. Now let's look down here at our answer. We have the first significant digit right here because there is a decimal in this number. So that's 1, 2, 3, 4, 5, 6, 7 significant digits. Okay, so we have to cut it off right here at this second significant digit. And we do that by looking at this third one and seeing if it rounds the second one up. It does not. So does that mean that we just make it 10? No, because 10 is not anywhere close to 103. What you do is you drop everything else. Everything else becomes zeros. So our answer then with the correct number of significant digits is going to be 100 centimeters squared. Uh-oh, there's no decimal point here, which means if we start counting on the right, find the first non-zero digit, we get 1. So this actually only has 1 sig fig. Well, if we think we're going to be smart and just go ahead and put a decimal point here, now there is a decimal point in this number. You start counting from the left, and the first non-zero digit is 1, 1, 2, 3. Now it's got 3 significant digits. So actually the only way to represent 100 with 2 significant digits is to turn it into scientific notation. So we go back up here, find our decimal point, and count over 1, 2. Okay, and then you write the first two significant digits. That's a 1 and a 0. So 1.0. Remember, the decimal point always moves behind the first non-zero digit, and the first non-zero digit here is 1. So we've got 1.0 times 10 to the, and then our exponent is how many times we moved the decimal place. And then we have to decide if the exponent's positive or negative. If the original number is greater than 1, then the exponent's going to be positive. If it's less than 1, it's negative. And of course 103 is larger than 1, so we get a positive 2 exponent. And then we just drop our unit down. So we end up with 1.0 times 10 to the second centimeters squared as our answer on this one. Alright, so let's just do one quick review here for dimensional analysis when our units have exponents. You're going to use your standard conversion factors just like you always have, but you're going to have to put those conversion factors in parentheses and then raise them to whatever exponent the problem was talking about. And remember, when you have something in parentheses and you raise it to an exponent, that applies to everything inside the parentheses. So that would include the number and the unit, which is why we did 1 times 1 and inch times inch. Alright, 1 times 1 is 1, and then the unit inch is actually raised to the first exponent, and then this unit inch is raised to the first exponent, and then your algebra property says that whenever you are multiplying something with the same base, then you can add the exponents together. Okay, so that's why you end up with inches squared, because 1 plus 1 is 2. So that's how come we end up with inches squared over here. And then, of course, we did the same thing up here with our 2.54 centimeters. You multiply 2.54 and 2.54 to get your 6.4516. And then centimeters to the first exponent times centimeters to the first exponent equals centimeters to the second exponent. Okay? Okay, so let's go ahead and work this problem here. This one is a complex problem. Alright, it involves units that have exponents on them. It involves our simple one-to-one units where it's not a derived unit. And since we're actually asking about gallons here, gallons is the English unit for volume, we will have to use our volume formula, which is length times width times height. Alright? And that's what gives us our units with exponents on it. The first thing that we're going to do is go ahead and apply that volume formula. You'll notice that you've got 7 feet by 15 feet by 9 feet. Now you can't put all three of those over one and try and run a problem. You could work it individually with each one of them and then add it all together at the end, but that's way too much work. So what we're actually going to do is we're going to find the volume in cubic feet first by multiplying 7 feet times 15 feet times 9 feet. And when you do that, the volume of this swimming pool is going to be 945 feet cubed. Okay? So that's actually going to be our given. Alright? This is going to be the thing that we put over 1. So let's go ahead and do that. 945 feet cubed over 1. Alright, and we're going to put our little dot and another bar. And the thing that we're trying to get to is gallons. Alright, we're trying to get to gallons. So, since we have feet cubed on top, we're going to have feet cubed on bottom. Now remember, when you have these units with exponents, you're going to use your normal conversion factors, which we have down here, and you're going to put them in parentheses and raise it to the exponent that we're trying to go for, which is cubed. So I see that we have 1 foot equals 12 inches down here. So that's the one we're going to use. 1 foot equals 12 inches. And since we have to cube this 1 foot down here, then we're going to have to cube this 12 inches up here. Alright, and keep going. So put another dot, put another bar. We're going to have inches cubed on the bottom. And then we look down here and we see that 1 inch equals 2.54 centimeters. So we're going to be able to say that 1 inch, and we're going to cube that, is equal to 2.54 centimeters, and we'll cube that also. And then we will add another dot and another bar, and we're going to have centimeters cubed on bottom. And notice here that as we went through the problem, we had feet cubed and feet raised to the third power is feet cubed, inches raised to the third power is inches cubed, so that matches. Centimeters raised to the third power is centimeters cubed, so that matches. So we're going to be able to say that 1 centimeter cubed equals 1 milliliter. And remember, that was one that you were supposed to memorize, as well as the 1 inch equals 2.54 centimeters. You're supposed to have both of those memorized by now. So we can cross that one out. And we'll add another dot and another bar. And since we've got milliliters on top, we have to have milliliters on bottom. And I see that 1,000 milliliters is equal to 1 liter. We can cross that one out. We're not to gallons yet, which is what we're after. So we keep going, add another bar. And liters on top means we have to have liters on bottom. And I see down here that 1 liter is equal to 1.06 quarts. Okay. And this is another conversion factor that you are supposed to have memorized. Right? So we can cross that one out. And we're not to gallons yet, so we're going to add another bar. And with quarts on top, we have to have quarts on bottom. So we'll look down here. The last conversion factor, 4 quarts is equal to 1 gallon. And we'll cross that last one out. Okay, so we ended up in the unit that we were trying to get all along. So that means we're done with the problem. We are ready to multiply on the top and divide along the bottom. Okay, so you're going to take, well actually I think first off what we need to do is go through, and everywhere where we have these parentheses with an exponent, we need to figure out what that number is equal to. So let's see here. 12 times 12 times 12 is going to be 1,728 inches cubed, right? And 2.54 times 2.54 times 2.54 is 16.38706.4. That is a terrible 6 centimeters cubed. And then, of course, down here, 1 times 1 times 1 is 1 foot cubed. And 1 times 1 times 1, 1 inch cubed. Okay, so these, and that's multiply sign between there and there. So really, in your calculator, you would say 9.45 times 1,728 and hit the enter sign or the equals button, and then you would have your whatever that answer is times the 16.38706.4, and then you can ignore these two ones here and then multiply by 1.06, and you can ignore this one over here. Now it's time to divide along the bottom. So the first non-1 thing is 1,000. So divide by 1,000 and hit enter, and divide by 4 and hit enter. And if you do all of that correctly, then you should come up with 7,090 gallons as your answer. Now, and I guess to be specific, well, it's gallons of water because the problem asked for gallons of water. Now you're saying, well, that's not what the calculator showed me. It didn't show me 7,090. This is with the correct number of significant digits. Again, you're going to look at the given to see how many sig figs you need, and that this number has no decimal point, so we start on the right hand side and find the first non-zero digit. So that would be 5, and then count everything after that, which is 4 and 9. So that's 1, 2, 3 significant digits. So over here, 709, that's our first 3 significant digits, because in the calculator number did have a decimal. The number that came after the 9 was not large enough. I think it was a 1. It's not large enough to round the 9 up, so it becomes a 0, and everything after it becomes a 0. So 7,090 gallons of water is how much that swimming pool can hold. So that problem really kind of encompasses most types of dimensional analysis that we would look at. And this video is running quite long, so I think we'll wrap it up here. Thank you for learning with me today.